Combustion analysis is a way to determine the empirical formula of a compound. Really, it's a way to determine what the ratio of carbon atoms and hydrogen atoms and oxygen atoms in a compound is. And so it's really a subclass of stoichiometry problem. So let's just dive right in and do an example. So let's imagine we have a compound and we're given that all it contains are carbon and hydrogen and oxygen. So we don't know what those subscripts are, but our job is to find out. So we're given that the compound just contains these, and we burn it, and we're going to burn it in such a way that it's a limiting reactant, and everything else is the oxygen's in excess. So we imagine taking this and some oxygen, plenty of oxygen, and when we burn it, we end up with just carbon dioxide and water, since we have excess oxygen and we don't get any carbon monoxide, and the hydrogen all ends up becoming water. Okay, now the reason this actually is something that you can do is there's compounds that react with carbon dioxide, and there's salts that absorb water, and so we can imagine taking the exhaust gas from this reaction and running it through a tube, and maybe part of the tube is packed with something like lithium oxide or something like that, and that'll react with CO2. So we can basically capture all the CO2 that's produced by the reaction. And there's anhydrous salts, like magnesium sulfate, that will absorb water, and so they'll suck up all the water basically, and so we can weigh the anhydrous salt before it gets the water and then after. So by looking at the weight gain, we can figure out the mass of water produced, and by looking at how much carbon dioxide reacted with the compound that reacts with it, we can see, okay, we know the weight gain was due to CO2. So basically it's easy to determine what the mass of carbon dioxide and water produced in a reaction like this is, and that's how this works. So let's suppose we're given that we took 80 grams of an unknown. Okay, so we don't know what this compound is. We have 80 grams of an unknown compound, and we're given that combustion analysis produced a certain mass of carbon dioxide and water. So let's say that we were given that we produced 117 grams of carbon dioxide, and it produced 48.1 grams of water. Okay, so this is the data we have. So we had our thing that absorbs carbon dioxide, we weighed it before and after, and this is how much weight it gained. And something that absorbs water, this is how much weight it gained. So the exhaust gas contained this much carbon dioxide and water. From that, we're going to be able to determine what the empirical formula, that is the ratio of x to y to z, is. Okay, let's go ahead and get started. So we can do this by realizing it's a stoichiometry problem, because we can see we don't know the formula here, but what we do know is that if we have x grams of carbon here, if we have x moles of carbon atoms, we're going to get x moles here. And we can see that for every 2 hydrogen atoms, we're going to get 1 water. So those ratios are what's going to allow us to figure out these numbers. Okay, so let's go ahead and start with the carbon dioxide. So we said that we had 117 grams of carbon dioxide. And in stoichiometry, we know we never want to work with mass, we want to go straight to moles. So we look at the molar mass of CO2, and so we know we've got 12 grams of carbon for every mole of CO2, and each oxygen is 16, so we multiply that by 2. We add that up, and we get that there's 44 grams of CO2 for every 1 mole of CO2. Okay, so we know we can cancel this. We can cancel grams of that. So now we've got moles of carbon dioxide. And what we really wanted was moles of carbon atoms. Okay, so if we look, there's 1 mole of carbon atoms for every 1 mole of CO2. So we'll write this conversion factor even though it's just 1. So 1 mole of CO2 is equal to 1 mole of carbon atoms. So we can cancel these units. We've got moles of carbon atoms, and that's what we wanted. And we do this, this comes out to 2.66. So that's moles of carbon atoms. Okay, so once we figure out the moles of hydrogen atoms, we'll be able to get that ratio, and I'll show you a trick to get the moles of oxygen atoms. Okay, we said we had 48 grams of water. We want to figure out how many moles of hydrogen atoms we have. So we've got to get rid of grams of water, so we see 18 grams of water. That's the molar mass of water. It's going to give us 1 mole of water. So we'll cancel grams of water to give us moles of water. And what we really want is moles of hydrogen atoms. So we can get that for our formula. So if we look at this, we can see that every mole of water has 2 moles of hydrogen atoms in it. So 1 mole of water gives us 2 moles of H atoms. Okay, so moles of water cancel. So we get moles of H atoms. Okay. So that's going to give us 5.3 moles of hydrogen atoms. Okay, so we can see there's more moles of hydrogen than there are of carbon in the compound, because remember moments earlier we saw that there was 2.66 moles of carbon atoms. Okay, but what about the oxygen? We can't do the oxygen directly because remember, if we go back to our combustion, we said that we had excess oxygen. So there's oxygen in the compound, but there's also we're putting in all this oxygen. So we couldn't capture the oxygen at the end because we put in all this extra. So what we're going to do is do it by subtraction. If we know how many moles of carbon and hydrogen atoms there are, we know what that mass would be, and we can subtract that from the total mass. So that's what we'll do next. Okay, so we get the mass of oxygen by subtraction. So we say we had 5.3 moles of H atoms, and we know that each atom is 1 gram of hydrogen per 1 mole of hydrogen. Okay, we could use more sig figs if we wanted to by using the empiric table. We'll just use 1. So that's 5.3 grams of hydrogen in our original compound. We also have 2.66 grams, or 2.66 moles of carbon atoms, and we know there's 12 grams of carbon for every 1 mole of carbon. So that comes out to be 31.9. Okay, so if we add that up, the total mass that came from carbon and hydrogen was 37.2 grams. And notice, if we go back to our original problem statement, we started off with 80 grams. So we can subtract that from the 80 to get the mass that came from oxygen. So the total was 80 grams minus, we have the carbon plus hydrogen, which we said was 37.2. So that comes to 42.8. of oxygen. So at this point, we can convert that to moles. We've got 42.8 grams of oxygen atoms. We know each oxygen atom weighs about 16 grams for every 1 mole. And getting a little sloppy with my notation here, we should say this is grams of oxygen atoms for every mole of oxygen atoms. And so we divide by 16, and we get 2.67.
moles of oxygen atoms. So we've got 2.67 moles of oxygen atoms for oxygen, and remember we had 2.6 moles of carbon atoms, and hydrogen we said was 5.3. So let's write all this out. We had carbon is 2.66, hydrogen we said was 5.3, and oxygen we said was 2.67. And that's obviously not a very nice way to write a formula, although it is a proper ratio, but we like to put these into integers. So the easiest way to generate a list of integers would be to divide all the numbers by the smallest number. So 2.66. When we do this, we get 1, we get 2, and we get approximately 1. So we write this as an empirical formula. We omit the ones. We always omit subscripts when they're 1. So we end up with this. So this is the empirical formula for a compound. And notice we call it this because empirical just means determined by experiment. And notice this doesn't mean that there's necessarily a molecule with 1 carbon atom and 2 hydrogen and 1 oxygen. It just means that's the ratio. So the actual molecular formula could be any integer multiplier of this. So you might be, right now it's 1 to 2 to 1. We could have it be 2 to 4 to 2, or 3 to 6 to 3, or something like that. Any of those would be valid molecular formulas that correspond to an empirical formula, because empirical formula is just a ratio.